All right, it is noontime. I'm gonna get started here. Um, so we are pretty much done with set theory, or at least terms with set, notations and whatnot, for a while. Okay, but this is not the last time we're gonna talk about, operations on sets, stuff like that. We'll get to it again when we get to how do you count cardinality. Basically, how do you count the number of elements in a particular set? That's an interesting thing, don't you think? Because you can have a set of integers, or a set of natural numbers, or a set of real numbers. There's an infinite number of those things in those sets, right? So how can you compare the cardinality or the number of elements in a set when they all have an infinite number of elements? So we'll get to that, okay? But in the meanwhile, we will get into, oh, this is MBTI stuff, so we'll switch to another screen. It's really kind of interesting, but it's not in the scope of this class, so I'm not gonna get into that. So let's get to 440. I'm basically following the outline, in the modules of 440 right now. And let me turn on that mic is that better? Yep, there we go. I'm not used to hearing my voice from outside, because what I'm hearing, from the speaker is transmitted by air. The normal way that I hear myself is transmitted by bone, which is a little bit different. So the frequency response is a little bit different. So that's why when I hear my voice from a speaker, it's like, is that me? All right, so we're done with set theory for the most part, and you have your homework. So your first homework is set theory. It is in the form of a quiz, but it's not a quiz. Okay, so you have until next week. Okay, you have until next Wednesday at noon to really turn it in. Okay, to submit your answers of the quiz. So it's not really a quiz. I mean, you can look up resources. You can read the notes again. You can even go see a tutor if you need to. But it's an opportunity for you to find out whether you are understanding the material or not. Okay. So if you're not understanding the material enough to answer those questions, don't just randomly pick an answer and hope that you are lucky. Okay, so instead, you can come talk to me. You can talk to another student. You can go find a tutor at the Maser or STEM Center. So those are all the resources that you have in order to try to figure out an answer. You can Google. You can do a Google search. Okay, you can go to Google and ask, what is the intersection of a set of two sets? Okay, and see how the other explanations work. Okay. So that's due in a week. Okay, so you basically have 168 hours to work on it. Is that okay? All right. Minus sleep. Okay, that's optional. Yes.
Is it timed once we open it, or can we open it however many times we want?
You can only turn it in once.
Right, but you can open it.
Yeah, so you can open it, work on one question, sign out of Canvas, go to another computer, sign back in, and continue the test.
Okay.
Yep. So it does maintain the state of the quiz as long as you do not submit it.
Okay.
But once you submit it, then you cannot you cannot have another attempt.
Okay.
Yep. All right. Any other questions about the homework assignment, basically? No questions. All right. So we're going to move on and talk about functions now. So many of you have some exposure to the concept of a function because you have taken classes already in math. Because Math 370 is the prerequisite of this class. So you probably have some exposure to the notion of a function already. But in this class, we look at functions a little bit differently. So we'll first get to this part here. We'll basically go back to tuples and just kind of refresh what a tuple is. So in order to define what a function is, or define a function as a set, we need to utilize the concept of tuples. Remember those things in round parentheses? Okay, those are tuples. And the first time we encounter those things is in module 0280. So you can right click on this one and open a new tab. But what a tuple really is an ordered container where components are ordered and the ordering is significant. So it's basically the same thing as a list or an array. Those are the programming concepts that kind of correspond to the concept of a tuple. So because of that, the tuple 112 is considered different from the tuple 121. Much like the array containing elements 1, 1, 2 is considered different from the array containing the elements 1, 2, 1. Is that okay? Are there any questions about what I just said? Okay, ordering is important, and you can have duplicate values. So you can see, 112 has one duplicated, 121 also has one duplicated. That's okay, because it is a tuple. It's basically the same thing as an array or a list. Is that okay? All right. So a 3 tuple is, has 3 items in it. This part here, we are not, well, I don't think we need to get to this part, anytime soon. But basically, within the tuple, you can use the square bracket notation, just like with an array, to indicate which element of a tuple do you want to access. Just like if you treat a tuple like an array, then the square bracket notation or the index operator makes sense, because it allows you to select, instead of saying, I want to refer to the entire tuple, now you can say, I don't need the entire tuple, I just need that item in the tuple. Yep?
Tuples are going to start at 0, right?
Yes.
Okay.
So everything is going to be 0 oriented, so the first item has an index of 0.
Okay. Oh, it says that. Makes sense.
Yeah. It's okay. I mean, it's a good question to ask. And it looks kind of strange, in computer science, why do we always count from 0 and not count from 1? The answer to that question is going to be clear in assembly language programming. All right, and we also borrowed the cardinality symbol, the bar thing, to basically say how many things are inside a tuple. And we don't really need that, anytime soon, but it is a notation. So now we move on to the discussion of functions. So we'll focus on one particular function here. We'll focus on this definition of a function, and I'm sure all of you know what this means, right? F of x is 2x. So f of 2 is 4, f of 1 is 2, f of -1 is -2, and so on. So are we okay with this concept? Are we feeling comfortable with the notation of what a function is? So in many ways, it's just a shorthand, okay? Because a lot of times your actual function definition is not just 2x, okay? It's a lot longer. So when the function definition is a lot longer, f of x can be seen as a shorthand, so you can refer to a particular function without having to write a lot of stuff, okay? But in this class, we look at a function as a map. So when you're dealing with a map, okay, in this case, it's mapping from something. It's mapping from what we call a domain, which is a set, to a codomain, which is also a set. So from here on, I'm not going to call a domain set, or codomain as a codomain set. A domain is just a domain, okay? It is implicitly a set, from the context. Is that okay? All right? So when you describe a function in this class, we use this notation to specify that f is a function, and it maps from x as a set, as a domain, to y as a codomain, okay? The exact mapping is not known, but we are defining what is the function, what is the domain, and what is the codomain. So that's the entire idea behind this notation. Do we have any questions about the notation that f is a function mapping x to y? No questions? All right. So now we get back to our example a little bit earlier. F of x is 2x. So if your function is f of x is 2x, then you have a few options, okay? Because do you want to deal with real numbers, Do you want to deal with complex numbers, or do you just want to deal with integers? That is a choice that you have to make when you choose your domain and your codomain. All right? So in this case, because in programming, most of the time we only need to deal with integers. So I choose to define our function f to map from integers to integers. Okay, so that's what it looks like, because this funny looking z is representing the set of all integers. So this, what I have highlighted here is saying that f is a function. It maps from integers to integers. There is no restriction of whether the codomain and the codomain can be the same or cannot be the same. Okay, they can be the same, they may not be the same. There are no inherent restrictions when we are talking about functions. Are we still doing okay so far? Still okay? All right. So the next step is, how do we spell out what is in that particular set? Because the whole idea, so this is where the notion of a function is going to be different from what you previously have exposure to. Because before, you just look at the function as a macro, right? It's like f of x is just expanding to this big gibberish, whatever. But from here on, in this class, we look at a function as a set. So in this case, you can see how f is a set because I use the braces to enclose the elements within that set. Okay? But what is in the set? It's a set of two tuples. Okay? So when you look at the two tuples, the first one is 0, 0, which basically means the value 0 from domain is mapped to the value 0 in the codomain. Okay? So the first element always has to come from the domain. The second element always has to come from the codomain. And the mapping is going from the first element to the second element. Is that okay? When you look at the second element of the set, now the ordering is not really important. I could have reordered the two tuples and it means exactly the same thing. But when we look at the second one in the way it is listed here, it is 1, 2. What it means is the value 1 from the domain is mapped to the value 2 in the codomain. That's all it means. Do we have any questions about this notation? Or do we have any questions about how two tuples are now used to express a function? Yes?
So that's just from f of x is 2x, right?
Yes.
This is just a different language for that, right?
Correct. So f of x is 2x up here is kind of a very concise way to say how the mapping is done. It is a mathematical mapping. When we look at this notation here, the one that is currently highlighted, it is really spelling out the individual elements of the function as a set. Is that okay? Because, yeah, go ahead.
Go ahead, sorry.
It's very
different from...
It is.
Yeah.
Well, the reason why it is so different is because a lot of times in computer science, your function is not going to be mathematically defined. Okay, I will give you an example later on because a lot of mapping that we conceptually have to deal with can be non-mathematical. In other words, it doesn't really correspond to a well-known mathematical definition. So we really have to spell it out like this, individually, which value from the domain is mapped to which value in the codomain. Okay, this example is kind of easy to define using the more traditional way. But in this class, we'll see opportunities where it is not the case. Is that okay? All right. But if you remember, the discussion from last time, we can also define, the same function using this notation, because what this is saying is x2x is an element of the set f. Okay, let me scroll that up. So this notation is basically saying if an element, if a value, okay, is a two tuple and it has the form of x and 2 times the value of x, and x is an element of z, then it is a element of f. And vice versa. If it's an element of x, it also has to have this property. Is that okay? So it's yet another way to express, what is in the set f in this case, but f is seen as a function. Are we still doing okay so far with these notations? Okay. So this one is, yeah, go ahead.
I just wanted to double check because I can't quite see the parentheses. Are both of those quantifiers on the whole formula on the right?
You mean
Below?
the below?
Yeah.
So this quantifier applies to the entire thing, and then this quantifier applies to also the entire thing.
Okay.
Yep. So the one that I've highlighted here is basically saying for each x in z, for each y in z, y equals to 2x if and only if xy is in f. That's yet another way to spell out what is in the function f. So I'm giving you all of these alternative forms to define f as a function that maps from integers to integers, where it is mapping a value to twice that particular value. Is that okay? So all of these is, in terms of what the function does, simple, okay? Doesn't do a whole lot. But what we are focusing on here is the notation, okay? So I'm using the same notations from the previous class, the quantifiers, the short form of listing elements in the set where there's an infinite number of elements and so on, because I want to use this opportunity to kind of reinforce all of those notations. None of that reinforcement is going to work unless you read the material again and do your own studying. But I'll try my best to kind of use these notations whenever it's appropriate, so that to give you guys more exposure to these notations. Yep.
So where in that notation can I see where negatives are included or are not included in the domain?
Okay, so how do we know whether negative numbers are included? Z itself is the set of all integers, including the negative integers.
Okay.
Yeah. So because of that, I know we are dealing with negative values from the domain as well. All right. So do we have any questions at this point about the way we look at a function as a set, and each element of the set is a two-tuple? So we are good with that so far? Okay. So now we get back to a more elemental question. What makes a function a function? Okay, I should have said what makes a set a function, but to make it more catchy, I use the question of what makes a function a function. So the first thing you might have noticed is, given the function is mapping from domain x to codomain y, we now know that if f is a function mapping from domain x to codomain y, then f has to be a subset of the Cartesian product of x and y. Is that making any sense to you? What is the result of the Cartesian product? The result of, go ahead. All possible pairs, where the first element of the pair comes from x in this case, and the second element comes from y. Well, doesn't every single element of a function meet that requirement? So that means a function is always a subset of the Cartesian product between the domain and the codomain. Okay? Now, I cannot say whether it's a proper subset or a subset of. Most of the time it's a subset of, a proper subset of, but occasionally it is equal to. Very, very rarely it is equal to, but there are cases where it equals to. So in general, I can only say it's a subset of. I cannot say it is a proper subset of. Is that okay? Well, if I claim that, okay, when do you think a function f is in fact the same, equals to the Cartesian product between the domain and the codomain? There's only one case well, not one, but two cases that is the case. So what would be those cases? They're very special. It has to do with very few elements. Yep.
If either X or Y or empty set.
Well, only one of them can be, well, they can both be empty, but if one is empty, the other one cannot be empty, depending on which one we are talking about. So let me just kind of go ahead and spell this out a little bit. So we go to accessories, go to mouse pad. Okay, there we go. So in this particular case, I'm going to use G, so we don't use the same function name. So if in G, you have one single element in the domain, let's say 1, and you say it maps to a codomain which also only has one element, let's say A, then in this case, G is also the same thing as the Cartesian product between the domain and the codomain. Because the Cartesian product only has one element in it, which is 1A as a two-tuple. But the function can only have also just one element in it, which is also 1A. So in this very special case, the Cartesian product is going to be the same as the function. Okay? What if we have more elements in the codomain, like AB, okay? Then it cannot be the case, okay? The reason why this cannot be the case is going to be explained later, okay? So we'll hold on to that one, until we get to that, the actual definition of what makes a function a function. So in addition to F being a Cartesian product between the domain and the codomain, there's another criterion that is really important. And in English, we're going to say it like this. Each element of the domain must be mapped to one and only one element in the codomain. Okay? That is the restriction spelled out in English. Is that okay? No?
Can you say it one more time?
Okay. So the highlighted text here says each element, so in a function, okay, as a set, each element of the domain must be mapped to one and only one element in the codomain. Yep.
Is that kind of like saying it has to, if it were numbers, it'd have to pass the vertical line test? You can't have something in the domain
That is correct. So when you look at it from the graphical perspective, then you have to pass that vertical line test. But so that's a very visual way to look at things. But I like the symbolic way of looking at things, which sometimes make it unnecessarily abstract and difficult. But that's what it takes to get through this class in discrete structure. So are there any questions about the English definition of this requirement? Does everybody understand what it means?
I was going to ask, does that mean, so can two x values then also equal the same y value?
Yes. So because it doesn't violate this particular requirement. This requirement, all it says is if I blindly pick something from X, okay, I take that element out of X and I ask, what is this map to according to F, okay, the function? It has to map to one and only one thing in the codomain. Can everything in the domain map to the same thing in the codomain? Yeah. Okay. Can a whole bunch of stuff in the codomain not map to? Yes, not a problem. Okay. The only requirement is everything in the domain, every single element in the codomain has to map to one and only one thing in the codomain. So that means you cannot say, oh, tech, here's an element from X, and it doesn't map to anything in the codomain. That would not be cool. Okay? Or if you pick up something from the domain, okay, and you say, oh, this thing maps to 3 different things in the codomain. That is not cool either. So that's why it is called one and only one. It is not at least one. It is not at most one. It is exactly one. So are we okay with that concept? Okay. I sure hope so. Let me check. Yep, it is streaming. The audio is good. So unless there's some technical difficulty on the other end, like the YouTube end or the Google end, I think it's good. You can always double check, by the way. For those of you with a cell phone and a earbud, you can actually go. Oh, you cannot because I have turned the default to unlisted, so you won't be able to see it until I publish it. Yep. Because I found out that some people, when they come in late, when they're driving, they would subscribe. They would actually listen to the lecture on their way driving to here. So I think that is a little bit dangerous. And I don't want to be on SAC B when there's a accident and then they say local professor live streams his lecture causing accident to happen, right? I mean. Okay, so now we can look at the English version and we ask, how do we use that note, all those notations that we have already encountered, to express the same thing? So all this stuff here is really just saying English is not exactly a very precise nor concise language. Okay, so what is the difference between precision and being precise and being concise? One, yeah, go ahead. One is there's no fluff, right? Concise means it is only as much as necessary. That's concise. Precise means it is correct. Okay, so English is neither. Okay, because there's a lot of way to misinterpret things. So we want to use more precise notations to do this. So I'm going to skip all of this stuff here. You're not supposed to. You're supposed to have read all of this before class. So we'll get to the final one, which is this thing here. So I'm going to scroll that up so that people can see it all the way from the back. So this is a condition, okay? It is either true or false, okay? So this whole thing is just a condition. It is either true or false. If it is true, then f is a function with a domain of x and a codomain of y, which is not listed here. Okay? If it is false, then x is not a function. It does not qualify as a function. So when you look at all this gibberish, okay, where are you gonna start? Well, you read it from the outside in, okay, not from the inside out. You read it from the outside in. The first thing we do is we look at this part here. Now, the codomain part is kind of important too, but what we are focusing on with this notation is the mapping. Okay, how can things be mapped? So when we look at this, the outermost thing that we need to first understand is the universal quantifier. In other words, whatever is specified in the parentheses has to be true for every single element in X. Okay? So let's say X has 20 elements, okay? And you found that 19 of the 20 elements meet this requirement, but there's one that does not. Well, I'm sorry. In that case, it is not a function. Okay? So every single element of the domain has to meet the following requirement. Is that okay? So the notation E in X is helping us to bind E, the variable E, to a particular element in X. So that means, in the discussion of everything in the parentheses, we are now focusing on one element of X, okay? So we are saying, okay, fine, so what property are we looking for, when we are looking at an element of X? It's this stuff here. So once again, you look at the outermost operator, okay? The outermost operator is really the equal sign here, the equality. So we are really just comparing something to 1. Does that equal to 1? Does the left-hand side of this comparison equal to 1? That's what I'm looking for. If it does equal to 1, it's good as a function. If it does not equal to 1, it is not a function. Okay? So now we are asking, then the question is, what are we counting then? What are we comparing to 1? So we see the bar notation. We see an open bar here. We see the end bar here. That's the sign of cardinality, which is basically asking, in between it has to be a set or a tuple, It's asking how many elements are in the set that is inside the bar notation. Okay? So we're basically just counting. So it boils down to what is in this set here, because we are interested in the cardinality or the number of elements of this particular set, but what are we talking about here? So now we go back to the notation of PQ, which means every element in this particular set has to be a 2-tuple. Okay? So as a 2-tuple, it has a first value, which is P, and a second value, which is Q. Okay, so what about P and Q? The first one has to equal to E. E is already bound, which means it is already selected or determined by the for all quantifier. So P has to be something from X. And Q, I really should have said that Q is an element of Y in this case, but the focus is how many things can be mapped, so I didn't do that. But there's an and here, and PQ is an element of F. So we are really counting the number of elements in F that starts with E as the first value of the 2-tuple. Is that okay? So I'll say that one more time, okay? So this whole thing is really just counting the number of 2-tuples in F that starts with a particular element in X, okay? So you focus on one single thing of X, and then you ask, in F as a set of 2 tuples, how many of the 2 tuples has this particular element as the first item of the 2-tuple? The answer should be 1. Not at most 1, because at most 1 includes 0. Not at least 1, because at least 1 includes 2, 3, 4, and 5, and so on. It has to be exactly 1. Yep.
So is that saying that everything within the domain should be different? Pretty much?
Well, yes, because the domain is a set. So that means all the elements of the domain are unique, because you cannot have duplicate items in a set. So that automatically guarantees that all elements of the domain are unique or different. Yep. Okay. So I'm going to put this scroll this all the way up, and then I'll use my text editor to give you guys some examples to consider. So here's the text editor, and we want to look at a few cases. I'm thinking about whether to change this to also specify that Q is in Y. If I change that, I'm going to change the other ones too. So I'm not going to change it just yet. And besides, this is supposed to be an additional requirement on top of F being a subset of the Cartesian product of X and Y, which automatically already says that the second element of a 2-tuple has to come from Y. So I think I don't need to specify that again. All right, so let's go through some examples. So in all of these examples, I'm going to use G as a function, and the domain is 1, 2, and then the codomain is AB, okay? And you have to tell me whether G as a set can be seen as a function or not, okay? So in the first one, G is 1A, and that is it. So is G a function? It is, okay, if it is a function, then I can, yes, go ahead. It is not a function, okay. So the answer is it is not a function, but let's see why it is not a function. If G was a function, then I can pick anything in the domain and say, okay, it has to map to one thing in the codomain, one and only one thing in the codomain. 1 meets that requirement, sure, okay, 1 maps to A, that's one thing in the codomain, no problem. What about 2? 2 doesn't map to anything, which counts as 0. 0 does not equal to 1, it fails that requirement. Is that okay? So if G is defined like this, it is not a function. Okay, let's look at another example. What about 1a and 2a? Is that a function? It is a function, okay, because there's no restriction that different elements in the domain has to map to different elements in the codomain. There's no such requirement. The requirement is everything in the domain 1 and 2, okay, each one has to map to one and only one thing in the codomain. A is one thing in the codomain. We're good. Is that okay? So let's take a look at another example. What about G looks like this? Oops. 1a and 1b and 2a. Okay, so let's put that back in here. What about this one? Does it meet the requirement? Does not meet the requirement, because when E is 1 in this notation here, then this set here now has two elements, because there are two tuples in G such that each one starts with 1. Okay, 1a meets the requirement, 1b also meets the requirement when E equals to 1. So the cardinality of that particular set equals to 2, it does not equal to 1. So it fails to meet that requirement. Is that okay? So this set is not a function. Are we doing okay so far? Okay. What about this one? 1a, 2b. Is that a function? Yep, it's a function. So are we good so far, to understand, whether something is a function or not? Because you can take a subset of the Cartesian product between, a proposed domain and a proposed codomain. That subset may or may not be qualified as a function. To qualify as a function, it has to meet this requirement on top of being a subset of the Cartesian product between the domain and the codomain. Are we good so far? Yep, go ahead. Which one?
5.
Line 5? Line 5 is not a function because when you look at this requirement here, now I know this is using f and not using g, but just kind of imagine this f is g, okay? So when E is bound to 2, which is an element of the domain, this set is now empty. Because if you look at this set here, no 2 tuple of this set has 2 as the first element of the 2 tuple. So when this set becomes empty, 0 is the cardinality, and 0 equals to 1 is false. Is that okay? All right, cool. So are we good so far? Yes? Okay. Excellent. So now we want to think of why the concept of a function is useful. I mean, this is a really obscure way to define a function, because you guys are used to, f of x is 2x, or some really complex mathematical definition. And this one is kind of arbitrary, right? You can basically make up a function that maps things all over the place. So why is this useful? So what I'm going to use here is an example to express the correctness of an algorithm that sorts an array. Then you go like, oh, this is pretty easy stuff. I mean, many of you have exposure to sorting algorithms in cisp 300, and then 400 again, and then 430 again, right? You know your sorting algorithms left and right. But what is special about this question here? How do we express that an algorithm is actually sorting correctly? In other words, I want you to give me an expression, a Boolean expression that's either true or false, okay? So give me a precondition of, the condition before a sorting algorithm starts. Give me the condition after, that actually qualifies the algorithm as actually getting the sorting part done. Okay? So how would you write that expression that basically spells out, yep, if this condition is true, that means the algorithm did sort the array correctly.
Also, it's already sorted in our mind,
Hmm?
and then we're coming up with the algorithm. It's not like an algorithm that you would use as your function is sorting the array. Does that make sense? That question?
Not exactly. So let's go ahead and read a little bit more here. Okay, so the first thing is, we might need to remember the values of each element of the array that you want to sort prior to the execution of the sorting algorithm. Okay, so we'll just use this notation here. So with this notation, I'm just going to click it so that we know, which condition we are talking about. So this is a precondition. It is given to be true. Okay. All we are doing is to look at the initial array before sorting, and we are just saying element 0 has a value of k0, element 1 has a value of k1, and so on. That's all it's doing. That's all it's doing. Okay? All it is doing is to have a way to name the original value of each element in the array, from k0 all the way up to k bar a bar minus 1. Remember, bar a bar is the number of elements of an array or set or tuples. So bar a bar is basically the number of elements of an array minus 1 because that's the last index of this is the index of the last element of an array. So is everybody okay with this notation? It really is just giving a name to the initial value of every element in the array. That's all. Okay? So given this is the precondition, how do you define the post condition that says, yes, this algorithm did sort the array properly? How do you define that? So I'm going to give you some alternatives that does not work, that is not true. Okay? So I'm going to use my text editor here. And actually, it's stated here. The first one is this one. Okay? So let me scroll up a little bit. So if I specify this as a precondition of the sorting algorithm, and it ends up making this true, does that make the algorithm a correct sorting algorithm? The answer is no, because to meet this requirement is easy. I just put zeros into every single element of the array, and that requirement is met. Is that sorting? Initializing an array to all zeros doesn't seem to be sorting to me. Well, it meets that requirement, but it's not sorted, okay? Okay, so that is not correct as a condition to qualify an algorithm as a sorting algorithm. What is missing here? Exactly, we have to find all the original values back, right? So, but we have to also get the right numbers because you might have duplicate values in the original values. If I had 2 16s in the array before sorting, I'm supposed to get 2 16s back when it is sorted. Does it make sense? Okay. Okay, so if that is not meeting all the requirements, what is going to meet that requirement? I'm going to add this new requirement here. Okay, so this looks kind of cryptic, right? If you look at all the subscripting and whatnot. Okay, so let's try to interpret this one. It says, as long as every valid index into the array, because 0 to bar a bar minus 1 are the valid indexes into the array. So for every valid index I into the array, this has to be true. A bracket I after the sorting algorithm has to equal to k subscript f of I. And f has to be a particular function. We haven't really talked about that word yet, but f has to be a bijective function. So if we can find, if this requirement is met, and this requirement is met, and f is a bijective function, then we can qualify the algorithm as a sorting algorithm. It can be any mapping, but it has to meet this requirement too. So it has to meet this requirement, and F has to be bijective. If all three requirements are met, okay, then we can say the algorithm is in fact a sorting algorithm.
So are those that function and then the requirement after that, are those the post conditions or are they added on?
All of these are post conditions.
Oh.
So this is a part of the post condition. This is another part of the post condition, and the fact that F has to be a bijective function is the third part of the conjunction of the post condition. So you're given the simple precondition, and then you have the conjunction of these, this, and F has to be bijective as the post condition. If the algorithm ends up with meeting with these requirements, then it is a sorting algorithm. Yep.
So what is it being bijective? Like, how does that help?
If it is not bijective, then they can all map to the same element. So that's the problem.
Okay, so it's just to avoid that mapping, they're mapping everything.
Correct. You have to map everything. Every initial value has to find its place in the final version of the array. Is that okay? Not okay? I'm turning some really simple concept of is it sorted into some gigantic mess of symbols.
Tell us about bijections later.
We'll talk about bijection next. Yes. So we'll deal with bijection later. But why do you think this is important? Why am I so tunnel visioned in terms of, I really want to express the correctness of a sort algorithm using conditions that can be evaluated. Why is that important? We all know what sorting means. Why do we need to spell it out, especially in these kind of obscure mathematical format? Why is that important? Anyone? Yep. It's AI. So how does it relate to AI? It relates to one particular field of AI. Which one is that? Theorem proving, automated reasoning, that sort of thing. Okay, but theorem proving is what we are dealing with here. I'm not sure. Did any one of you take? Okay, English grammar does not make sense to me, but we'll try to go with the convention. Did any one of you take cisp440 with me? You did. Okay, that must be some time ago, because I haven't taught that class since 2016, so it has been a while. But in that class, oh, you did too? Did you remember, we went through some, derivation, like, there's an algorithm here, this is a precondition, we can derive a post condition based on the statements in between? Yeah. So that's basically how we can derive the post condition without running the program at all, without using a single test case. Okay, you can give me the precondition. Mathematically, I can say this condition has to be true as the post condition of this chunk of code. Okay, I do not need to rely on individual test cases. I can give you the quote-unquote universal truth as a mathematical expression that has to be true. If this is the precondition, this is the chunk of code, this has to be the post condition. Okay? So with a sort algorithm, if the post condition can imply this, and F is bijective, then I say the algorithm is a proper sort algorithm. I don't need a single test case anymore. Okay? What is the problem with testing an algorithm using test cases? Yep.
It could work right a million times, and then the millionth and one time it could not work.
There's no guarantee, right? Because it's not a probability kind of thing. Because when you're testing, okay, so let's say you're testing a sort algorithm, okay, because we are talking about that. So you can try all the different permutations of values, in the initial array, and everything seemed to work, okay? And then you conclude, yeah, it has to work because I have tried almost everything. And then you try to put two duplicate values into the array, and it doesn't work. Because you might have missed a certain condition in the sort algorithm, and it doesn't take care of what if you have two values in the array that are the same. okay? So there are boundary conditions and all kinds of conditions. So the way you look at this is if you are trying to, okay, the best way to look at this is to look at it like throwing darts. Okay, so I'm going to give you a kind of graphical representation or an analogy of testing a program by test cases. This is not directly related to cisp440, but in general, it is a very important concept to understand. Okay, so it's difficult to write it, because this is actually just a plane. So what I'm going to do is I will first draw a sheet here. Okay, so this sheet is really representing what works and what does not work with an algorithm. Okay. And I'm going to, I don't think it has a way to paint with a shape. Okay, so I'm just going to say, it is for the most part green, okay? Green means good, okay? Green means, those cases work without a problem, okay? There are only a few spots that is not green. Those are the cases where the algorithm does not work correctly. So I'm going to scatter some of those spots here, 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 and here. Okay? So you look at this and go like, oh, clearly the algorithm does not work. But that's because I give you the answer already. Okay? So now you have to kind of imagine that you have another sheet, opaque sheet of material covering this part here. Okay? So you don't really get to see the green and the red, okay? All you see is the front, which is black and it's opaque. You cannot see behind it, okay? Every time you throw a test case to the program, it's like throwing a dart at the whole thing. And you put a dart out and go like, okay, is that spot behind the dart hole green or red? Green, good, okay. Throw another dart. Is it green or red? Green, good. Throw another dart, and so on. So you can throw a lot of darts, okay, and they all land up on a green spot. Is that a conclusion that the algorithm will work in all cases? No, because you're just lucky that you have missed all the red spots. When are you going to land on a red spot? It all depends on the test cases, right? And if you are the person who wrote the algorithm to begin with, it is very unlikely that you will even think about this spot may be red, because the way you code it is you have already forgotten those cases. And that's why the program started off with a flaw to begin with, is because when you wrote the program, you forgot about those cases. When you are testing the program, you're likely to forget about those cases as well. Is that okay? Yep.
So you want to provide us with a solution of, okay, even if we don't know what test cases we should use,
Yeah.
we can always, before you even write the code,
Yes.
try
So,
and map it out mathematically.
yes. So the solution that I'm giving you is basically asking a question. Are there red dots? And it comes back with either true, yes, there are red dots, or no, there are no red dots. If it comes back and say, yes, there are red dots, well, you better go back and fix your program. It doesn't tell you where it's wrong. It just tells you that it doesn't work with all cases. That's all. Okay? But it can also come back and say, everything is green, it's good to go. Then you don't have to throw a single dart, because I have mathematically proven that this entire thing is green. So now you feel confident to release that code.
At the very least, we will think about, okay, I need to use this test.
Yes. Yep. Okay, so, yeah, go ahead.
I was going to ask, so like, where's the interaction between like an algorithm you came up with and your actual formal conditions? Because if you just have the conditions, you can't like relate those back.
Correct. So you need automated theorem proving in order to derive the condition, the end condition or the post condition of your algorithm based on the precondition. So that's the difficult part, because if you have a $50,000 line program, it's going to take you a long time to derive that. It's not like it's not possible. It's just that it is difficult to do. Okay. So how does this relate to what we are talking about? In other words, we are looking at a very easy to understand picture. Okay, we have a green canvas with occasional red dots. Okay, easy to understand. Okay, how does this relate to all of these obscure symbols and abstract concepts that we are now talking about? Where's the connection? The connection is these conditions is what you use to say green or red. Is that okay? And that is why it's important. Because until you can tell a computer in a formalized language and define what is green and what is red, you cannot ask the question, is this algorithm working correctly? Okay? What is the problem of not having a mechanism like this? What is the problem of not having a mathematical way to prove an algorithm is correct once and for all? Okay, exactly. And so what can possibly happen when you release code that is not proven to be 100% correct? It can crash, okay, yes. We encounter crashes all day long as the crash is not on a control system of a nuclear plant. For the most part, we'll live, right? You might lose your homework and have to redo the last hour or so or something like that, but we'll live. You want to add something to it? People can get hurt, like if the railroad crossing control system is not working, it doesn't put the bar down when it's time. Yeah, people can get hurt. Yep. People can exploit it. I like that. So I'm going to give you this. I'm not going to give you a whole lot more than just giving you a link to it. But this is what happens when you do not check your software. Okay? Heart bleed. Okay? I will leave it up to you guys to read what it is. How many people already know what this is, at least superficially? Very good. But if you read about it, it's a bug in the program, okay? But the consequence of that bug is really, really bad, okay? Because a hacker can basically keep pinging a server, and it's probabilistic, but sometimes it can return back with sensitive data. Okay, like the key, encryption key of some of a website and stuff like that. But it happens only because whoever was writing the SSL library did not go through the formalized verification process and only used test cases. And this is a very good example of hacking. How many people here are interested in hacking? You don't have to have your hand up if you don't want to, be identified, okay? I'm going to raise my hand, okay? It's just out of curiosity. I think it is interesting. It's fun, okay? I have no malicious intention because if I did, I would be really rich already by now, and I wouldn't be teaching here. So by using that as a counter example, I have proved that I'm not a black hat. Because if I were, I wouldn't be here. So anyway, where was I? I forgot. Okay, now I need to backtrack. My stack needs to unfold. Yes.
You're asking if we were interested in
Oh, right. Okay, very good. Okay, so if you're interested in hacking, okay, where do you start? I know I'm digressing a little bit more and more from the original topic, but this is important too, okay? So if you were a hacker, where do you start? Go ahead. Something easy, okay? I would look up standards. Okay, I would look up all kinds of standards, especially protocols, networking standards, networking protocol standards that allows one computer to talk to another computer, okay? But I would specifically look for certain things where a particular field of the protocol says it can be length delimited, okay? It can be up to a certain size, which means it's length delimited, that's a maximum size, but at the same time, it's also null terminated or terminated by some particular special character. Okay? The reason why it would look for that first is because a law-abiding, really stand-up and good programmer would make an assumption that everybody is also law-abiding, of conforming to the standard and everything. Okay? So their assumption is if this field can only have up to 256 characters, people would play by this rule. I only have to allocate a buffer of up to 256 characters to hold the content of this particular field when I'm processing it. Okay? So they will make that assumption first, allocate a buffer of exactly that size. Okay? And then because they make the assumption that everybody is playing by the rule, they can now say, oh, a string copy will work just fine. Okay? I can keep copying until I see the null character because every packet is well formatted. Guess what? They're not. Because tag will be the first person to say like, I wonder if I give this field 512 characters, which means it's 256 more than what it's supposed to be, before it encounters a null terminator, I wonder what's going to happen with that program. So I'll send a packet over. Okay, if the software is properly implemented, it would just say rejected. If it does not meet this requirement, done. Not going to talk to you, right? On the other hand, if it crashes, then they go like, well, if it crashes, it means it's overwriting something on the stack, and that's why it's crashing. If I can control what is being overwritten on the stack and how it is being overwritten, I might get control. I may gain access to this particular program. So then I can look further into it and further into it and further into it. I might actually find a way to do it. That's how a amateur hacker is going to think. Now think about the professionals. Okay? So this is why it is important to have programs to be verified automatically using a program so you can mathematically conclude this is correct. It will get a job done correctly. Yes?
You still have the same problem if your preconditions don't account for those cases too.
I don't understand.
Like if you had a precondition that
You have no condition. Basically, you have to throw away the precondition that the packet is well formed.
No, what I'm saying is that you still have the same problem if, like, say you had a precondition that was like, oh, they're only ever going to send 256 bytes at once, and it can still be, your algorithm can still be provably correct, but would still fail.
Correct. So if you start with I'm trying to think of the word to describe the precondition. If you start with a precondition with an assumption that people are playing by the rules, then it won't catch these exception cases. That is correct. So you have to relax your precondition to basically say the incoming packet can be anything. So can I either recognize the packet correctly or reject the packet because it doesn't meet all the requirements? So that's what you need to do. But nonetheless, to test all of that, and by throwing random packets, to the program is not going to work very well. Proving it by mathematics is going to be the way to do it. Okay. Now this is an interesting field because, let me just kind of throw that term up here, automated theorem proving. There are several names to all of this stuff here. It has been a big topic in the past. So when I say in the past, it's about in the 80s, to the early 90s. It was kind of like a big thing. AI, artificial intelligence, was a big thing during that time, and automated theorem proving was kind of the same thing. People were very excited. They wanted to do all this stuff. They saw value in it and so on. And then at some point they ran out of processing resources. Because back in those days, computers are not nearly as powerful as they are today. Okay, I'm not going to repeat the joke of that I used in CISP 310 last night, but it suffices to say that the progress in terms of transistor size, speed of processor, how much RAM, how much storage that we have from even just the 90s to today is tremendous. things that we thought, nah, we can, in theory we can do this, but in practice there's no way we have enough processing resources to do it in the 90s. Today is like my Fitbit can do it. Oh, I am exaggerating a little bit, but you get the idea, okay? So automated theorem proving is one of those things. So it died in the late 80s or the early 90s because we didn't have the hardware to do it. We just did not have enough horsepower to even come close to doing it in a practical sense. But now we do. Now we have all kinds of processing resources that was not undreamed of in the 90s. So suddenly this field is now alive again because not only do we have the hardware to do it, we also have the demand to do it. Okay? In the 80s, okay, what is the worst thing that can happen when you have a disk with a virus that can infect a computer? How fast can it spread? It depends on how fast you can run. Because you have to put that disk onto the next computer, put it in. Okay, next one. Keep doing it like this, right? So it can only spread so fast because it's physical. But these days, well, think about IoT. What is IoT? The Internet of Things. So think of all the things in a household that can potentially hook up to the internet. Your washer, your laundry washer, your dishwasher, your oven, your stove, your refrigerator, your microwave. Everything is going to be IoT'd. So what that means is they can all be hacked. Yes, you can hack my toaster now. And that makes this kind of problem, okay, let me go back to this one here, even more problematic. Okay, before the internet was around, but it was only accessible to government agencies, universities, and the speed was only like this much. Okay, so the worst you can do is to infect a few computers, and people were not using computers that much anyway. Okay, but these days you can take down major utility services if you can hack into, say, the smart website, or the power distribution is now controlled. It's smart, okay, and that really is the most dangerous place to get hacked, because once you cut down power, think of what's going to happen. Riots, stuff like that, because if you cut down power for 2 or 3 days, how can the police department communicate with all the patrol cars? They might have a diesel generator, but they have no way to communicate with another precinct. They will have limited ability to communicate at that point. So, so power distribution is a big thing, and they are now on the web. Okay? So if you have not considered computer security in your future, career, well, keep an eye on it, okay? I'm not saying everybody should get into computer security, but it's a very interesting field. It's changing really rapidly. You can say, oh, but game industry is kind of the same thing. Well, okay, has anyone met a real game programmer, a game developer? Okay, are those people happy? Why are they not happy? Because game developers are, quote unquote, a dime a dozen. Okay, at least because it doesn't take much to become. Now I shouldn't say that because I'm not one, but to become a game developer, you do have to understand Unity, Unreal, and so on and so forth. But those are not really particularly unique skills. So a lot of people can also acquire the same skills. So now you have a market with a lot of qualifying people, but the job positions is not really that many. Okay, because once the game engine is done, okay, most of the development work is really done. So most of the effort of these game companies is spent on what? So you can look at Riot, okay, the League of Legends, okay. They tweak all those champions a little bit, so there's a little bit of coding there, but what do you think is consuming most of the expenses or resources of Riot? Skin design, okay, developing new champions, having specials for Valentine's Day, specials for Halloween, specials for Christmas, and so on and so forth. None of that, or very few of that, actually involves development. It's not coding. So kind of think of it that way. When you're into computer security, and let's say you're good at it, okay? Do you think you'll be being bounced around, and to look for jobs? Think of it the other way around. Okay, you're the employer. So let's say you're Wells Fargo, okay, and you have a team of computer security people. They are proven, they're good, okay. Do you think you want to nickel and dime with these people on an annual review?
No.
Why not?
Your business depends on it.
Well, there are many reasons why not, right? The first one is if you nickel and dime these people, they just knock on the door of Chase, okay, and go like, well, these people are nickel and diming me, can you give me a raise, like 10%, okay? And Chase is going to go like, yep, you're proven, you know how to do it, you clear all the security clearance, check, okay, come on over, okay? So they can be, easily moved on to another position because it's valuable to most of the banks. But you can also think in a way where these people are not particularly law-abiding, okay? So they're hanging on to this job, because the pay is good, okay? But now they say, well, I want more pay, okay? And the bank says, no, we are going to put a cap to how much you can make. Some of these people will turn into black hats because they got the skills, they got all the inside information, and so on and so forth. And when they turn black, they can make a lot more, potentially. I mean, the risk is bigger as well, but there's a break-even point to the mentality of these people. So banks will basically go like, okay, we have to keep these people employed. We have to keep them happy, okay? We have to make sure that they make enough money that being a black hat is enough of a risk so that they don't do it. Does that make sense? Because this is psychology. This is just how people think. As opposed to in the gaming industry, okay, you get fired by one game company, the other one goes like, well, I can pay you less than what you used to get paid because you don't have a choice now. Does it make sense? Okay. Now, if you're a computer security expert and you work for the government, especially at the federal level, they may not even let you leave the country. Think about it. I don't know. I have never really got to that level. And I don't know people at that level, but I know they do a lot of security check of all kinds. If you want to work for a national lab, they have all kinds of questions, all kinds of clearance that you have to deal with before you can start working. Yep. And I think some of you guys may have worked for the military branches, so you have an understanding of how much they have to go through in order to make sure that they can trust you. So kind of good stuff to think about, even though it's not directly related to this class. But in a very strange way, they are all related. Okay, so we have 5 minutes left, so I'm going to go ahead and finish this stuff. Okay, so we are pretty much done with this particular slide, but what we'll do on next Monday is to continue, and then we'll start to talk about injection, surjection, and bijection. So these are properties of functions. So given that f is already known to be a function, it meets all the requirements of a function, then we can start to ask these questions. Is it injective? Is it surjective? Is it bijective? Bijective means it's both injective and surjective, okay? So these are special properties of functions. And when we get to bijection, it is really cool because anything that is bijective also has a reverse, has an inverse function. It's reversible. Okay? Now, reversibility is really a big deal, especially in computer security. Okay? Do you guys know how your password is stored on a server? Okay, first of all, it is not stored as plain text. Okay? So if my password is secret, it is not stored as secret. Because if it were, anyone who hacks into a server, get into the database, they can now grab all the passwords and they can now authenticate into anyone's account, right? So that would not be a good idea. So how do you think passwords are stored? Yep. I sure hope they're not stored as plain text. Okay, so let's say you're a responsible company. So that's an assumption. We'll make that assumption. So if you are a responsible company, how are you going to store the passwords of your users? As a hash. Okay? So a hash, basically, if you have taken 430 already, hash tables, it's the same kind of a hash function, except a MD5 hash will give you a pretty long string, okay, of zeros and ones, okay? But it is still a finite length of zeros and ones. In other words, there will be multiple actual passwords that map to the same MD5 hash. Okay, it's just mathematically speaking, that's going to happen. Okay, but because the hash is supposed to be really long, okay, so that means to find out what string maps to a particular hash is going to be difficult. Okay, it can be done, but it's going to be difficult. Okay, so when in the 80s and 90s, when Linux and Unix were first, becoming operating systems and stuff like that, MD5 hash was sufficient because people did not have enough processing power. If they did, they do not have enough storage to kind of remember what string maps to which unique, MD5 hash, which string maps to which MD5 hash. So if you steal the MD5 hash password file from a server, it doesn't do any good, okay? Because all it says is whatever the original password is maps to this, really, really long, string of characters that are kind of random, okay? So reversing it, because we are talking about reversibility, so reversing it is not an easy thing to do, okay? Looking at the hash, you cannot really find out what characters, what actual string is going to map to that hash. But now it's different, because now we got massive processing power. We also have massive storage capability. So someone just said, I'm just going to generate all the possible hash values, and I'm going to store everything in a table. So now, if you can get the hash table or the hashed password file from a server, you can now easily reverse the whole thing and find out what string can generate that particular hash, and then you can get into people's account. So that's why MD5 hash is no longer considered secure. Even with salting, it is still kind of like that. Okay. So they're moving on to additional, longer and more complex, hash functions now, in order to store passwords, into a database and stuff like that. But that's going to be changing all the time, because we are increasingly getting more and more processing power, and we are also getting increasing amount of storage as well. So what was secure is not secure anymore. What is secure today may be obsolete and not secure in 2 to 3 years. Okay, so that makes security a very interesting field because it never sits still. It always moves. To end today's lecture, we got 1 minute. One student in my 310 class told me today that they can now make transistors down to 1 nanometer as a research project, but it's not going to be long until they incorporate that into real processors. Okay, so with smaller transistors, they become faster, and we can pack more computational circuits into the same area using the same amount of power consumption. So you can expect computation power to continue to increase like Moore's law. So I'm going to end today's lecture with that note. I'll see you guys on Monday, and have a nice weekend.